Today we're going to talk a little bit about the strength of acids and bases. So far we've only actually talked about strong acids and bases, so today I'm going to tell you that they can have different strengths and what that means. So the first thing that we're going to talk about is just a refresher on what dissociation is. So if you remember from the last chapter, dissociation is just when a salt separates into its ions. And that's the same thing for acids and bases. When an acid or a base dissociates, it just separates into the ions that you get. All right, so a strong acid is a strong electrolyte. It would be an acid that separates completely into the H plus and then whatever the conjugate base is. So hydrochloric acid would be one example of that. So it separates completely when it dissolves to H plus and Cl minus. There's not actually any HCl left in that solution. Weak acids, which we haven't really talked about explicitly yet, are ones that are weak electrolytes, so they don't separate completely. So one example of this is vinegar, which is acetic acid. So when it dissolves in water, some of the H plus is donated, but not all of it. And then one additional term I just want to cover, and we looked at these a little bit in our activity the other day. Diprotic acids are acids that have 2 protons to donate. So 2 H pluses could be released. And there are also triprotic acids. You looked at this. Phosphoric acid is one example of that. Right. So with bases, it's the same thing, or it's analogous. So strong bases are ones that separate completely. An example of this would be NaOH. It separates completely into Na plus and OH minus when it dissolves in water. There's no NaOH left in that solution. Weak bases are ones that don't separate completely. So NH4 or NH3, is one example of a weak base. So it will take some protons, it will accept some protons from a water molecule if it's dissolved, but not all of it. So you'll still get some molecular NH3 present in your solution. Right, and so this is just a table which you can find in your book, and it tells you about the strength of acids compared to each other. So at the top here we have acids that are very strong. They dissociate 100% when they dissolve in water, and then down this end of the chart we have weaker acids. Okay, some of them will be a mixture of ions and the molecular form of the acid, and then some of them, like these down here, dissociate very, very little. Okay, and then the same thing for bases. Up here are the ones that barely accept any protons at all when they're in solution, and then down here are ones that are very strong. And what you'll notice is that each of these are conjugate acid base pairs. So HClO4 is the acid form, and ClO4 minus is the conjugate base. So the stronger the acid is, the weaker the conjugate base is going to be, and the stronger the base is, the weaker the conjugate acid is going to be. So this relationship is inverse. All right, so as an example, does the equilibrium mixture of the following reaction contain mostly products or mostly reactants? So we have H2SO4 breaking up or combining with water to break up and form H3O plus and HSO4 minus. So if we go back to our chart, you can see that H2SO4 is a strong acid, which means that this reaction is going to go pretty far toward the products, okay, because H2SO4 is going to donate most of its protons. So in this case, we'll have mostly products in our mixture. And you can use that chart that I just showed you to determine that relationship. We can also determine this relationship with dissociation constants. So Ka and Kb are just the equilibrium constant for an acid or for a base when they're combined with water. So just like when we did Kc in the last chapter, this is the same thing. We're just now applying it to acids and bases. So for an acid, if we use our generic acid as Ha, and we combine it with water, it will break apart and make H3O plus and A minus, okay? And we can write the equilibrium constant for this reaction as the concentration of A minus times the concentration of H3O plus divided by the concentration of HA. And we wouldn't put the concentration of water in there because it's a liquid. All right, and then we can do the same thing for a base. So the base dissociation constant is based on the equation B plus H2O yields BH plus plus OH minus. And so we can then write our equilibrium expression as BH plus times the concentration of OH minus divided by the concentration of B, where B is our base and A is our acid up here. Okay, so this is just an introduction. We're going to do lots of practice problems with these, and so you can get really good at them.